Okay, so we're going to do some standard solutions and dilutions notes. So technologists in a number of industries often need to make solutions with a specific concentration. In the field of healthcare, prescriptions can involve either creams or liquids that require an exact amount of medicine solute to be combined with the appropriate solvent. During manufacturing, specific solutions may have to be prepared. Each solution is an essential component, allowing the precise control of a chemical reaction. So why don't these facilities simply order the necessary solutions already mixed in the proper concentrations? So as in the case of consumer goods, it is less expensive to ship highly concentrated solutions. Another reason is that sometimes solutions need to be modified. This provides greater flexibility when it comes to mixing the specific solutions needed for specific situations. Clearly, in many industries, technologists follow careful procedures to prepare standard solutions. So, making a standard solution requires practice and skill because the slightest error can cause the concentration of your standard solution to be less accurate. So in the next investigation that we're going to do, we're going to have an opportunity to produce a standard solution and then to dilute the solution. So standard solution is a solution having a precisely known concentration. Now, diluting solutions. So some chemical solutions are transported in a concentration form to save costs. It may be necessary to dilute such a solution to obtain a solution with a specific desired concentration. There are also times when water is removed from a solution to make it more concentrated. And in each case, the amount of solute is unchanged, but the amount of solvent changes. So, adding solvent to a solution. So when a solvent is added to a solution, the number of moles of the solute, or N, is what is unchanged. So because of that, we can take our equation and we can manipulate it. So we can go from C equals N over V, okay? We can multiply both sides by our volume, and we can get that the number of moles is the concentration multiplied by the volume. Now, if the number of moles is staying the same, we can manipulate this then to say that C1 V1 is equal to C2 V2. And this is our diluting concentration. It's also shown as CI VI is equal to CF VF, which is saying the initial concentration and volume, the number of moles is equal to final concentration and volume. Now it says here that we need to note that the final volume is the total volume of the solution, not just the amount of solvent added. Okay, so that's very important, especially when we look here at our example problem. It says here you have 65 milliliters of a 0.759 mole per liter solution of sodium chloride. We need to A, calculate the final concentration of the solution if it is diluted to a final volume of 100 milliliters. Then we need to calculate the final concentration of solution prepared by adding 100 milliliters of water to the original solution. And then how much water do you need to add to the original solution to obtain a solution with a concentration of 0.200 moles per liter? And then finally, how much water needs to evaporate from the original solution in order to obtain a solution with a concentration of 0.890 moles per liter. So let's look here. We've got for A, which is calculate the final concentration of the solution if it's diluted to a final volume of 100 milliliters. So what we need is, or what we know is the initial volume, which was 65.0 milliliters. We know the initial concentration, which was 0.759 moles per liter. Okay, we know the final volume is 100 milliliters. Okay, and what we need to figure out is the final concentration. So I take my formula here of CIVI equals CFVF. Okay. I'm looking to calculate for concentration final. So I just have to divide, in this case, both sides by the final volume. And I get that the concentration of the final is equal to the concentration of initial times volume of initial divided by volume of the final. So I'm going to sub in my values. So concentration of the final is going to equal 0.759 moles per liter multiplied by 0.6, oh, sorry, yep, 0.65 liters. Okay. Oh, no, that's not right either. It should be 0.065 liters, all divided by 100 milliliters, which, if it's 100 milliliters, it's 0.100 liters. Okay, and my liters cancel out, so my concentration final is equal to 0.493 moles per liter, putting that lovely thing in my calculator. And if I look here, it says the final concentration of the solution is 0.493 moles per liter. So, B, it says to calculate the final concentration of a solution prepared by adding 100 milliliters of water to the original solution. Well, that changes things a bit in comparison to A. We still have the same initial volume of 65.0 milliliters. We have the same initial concentration. But now the final volume is 65 milliliters plus, because I'm adding 100 milliliters, this now becomes 165 milliliters of solution. And so we're looking here again to calculate the final concentration. I'm going to manipulate my equation again, just to get into the practice of it. If we knew this equation off by heart, then we could do that. But it's always good just to know the one and be able to manipulate it, okay? So the concentration final is concentration initial times volume initial, all divided by the volume of the final. So that becomes my concentration of final is equal to 0.759 moles per liter times 0.065 liters, all divided by, oh, there's my line, all divided by 0.165 liters. And I then end up getting a final concentration of 0.299 moles per liter. And if I look here, the final concentration of the solution is 0.299 moles per liter. So C said, how much water do you need to add to the original solution to obtain a solution with a concentration of 0.200 moles per liter? Well, I still have the same volume initial of 65 milliliters. I still have the same initial concentration, moles per liter. Okay. Now, this time I'm solving for my concentration of final. Okay. Or sorry, I know my final concentration because that's what I'm trying to get to. Okay. And it's the volume final that I'm trying to calculate. So I then have to look at what's the volume added, because that's what the question really asks you for. Okay, so C1V1 equals C2V2. We now have to, or sorry, F, we now have to manipulate this in order to solve for the final volume. Okay, so I'm going to take this and I'm going to divide it by concentration final. What I do to one side, I have to do to the other. So my volume final becomes my concentration initial, volume initial, all over concentration that I finally want at the end. Now, I will then sub into my values. So my volume final is going to be 0.759 moles per liter. Okay, and I'm going to multiply that by 0.065 liters. And then I'm going to look at the final concentration I want. Okay, cancel out those. I'm going to get 0.246675 liters. Okay, now we need to keep in mind that the amount added, okay, can be found by subtracting the initial volume from the final volume. So volume final minus volume initial is going to equal the volume added. So I'm going to take 0.246675 liters and minus 0.065 liters, and that should give me 0.181675 liters, or 181.675 milliliters. Because if I look back here, I've only got 3 significant figures, 3 significant figures, and 3 significant figures. I need to report my answer in 3 significant figures, so it should be 182 milliliters if I'm going that way. So you need to add 182 milliliters of water. Finally, we've got D here, and D says how much water needs to evaporate from the original solution to obtain a solution with a concentration of 0.890 moles per liter. So essentially, we still have the same initial volume, and the initial concentration is the same. Sorry, let me write here, 65 milliliters. Okay, concentration initial is still 0.759 moles per liter. But now my concentration final that I want is actually 0.890. So it's actually higher than my initial concentration. So I need to calculate the volume final, and then I need to calculate the volume evaporated. Okay, so concentration initial, volume initial is equal to concentration final times volume final. My volume final is concentration initial, all right, divided both by concentration final. Concentration initial times volume initial, all divided by concentration final. All right, so this now becomes my volume final is equal to 0.759 moles per liter times 0.065 liters, all over my final concentration of 0.890 moles per liter. Okay, cancel out my units, and I should get a volume final of 0.05543254427 liters. So it says the amount evaporated can be found by subtracting the final volume from the initial volume. So volume evaporated equals the volume initial minus the volume final. So the volume evaporated becomes 0.0065 liters minus 0.055432, etc. liters. Okay, and then that should be equal to 0.00 9, sorry, 9, 5, 6, 7, 4, 1, 5, 7, 3 milliliters. Okay, and because if I look here, here I have only 2 significant figures, or sorry, I have 3. Either way, I have 3, so let's round it up. Here goes, here can be my 3 significant figures. So I'm going to report, well, let's report it in milliliters, shall we? So 9.57 milliliters. And if we look here at the answer, the volume of water needed to evaporate is roughly 9.6 milliliters. Not too sure why they reported it to only 2 significant figures when there is 3 in the entire question, but hey, that should be all right. So that is the end of the units for the General Learning Outcome 1. You guys will get another unit pack for the continuation of the other learning objectives for this particular unit, as well as the rest in the course. Thanks for listening.